So in this video, we're going to continue our discussion with sequences. And in the last one, you saw that given an nth term formula, we could generate the terms of a sequence by simply plugging in the domain of positive integers, the 1, 2, 3, and so on. Now we're going to work the other direction. We're going to go ahead and be given a sequence, and now it's our job to write the nth term formula. So write the formula that would generate these numbers, where this would be our a sub 1, our a sub 2, a sub 3, a sub 4, and so on. So when you start a problem like this, there's a few things to keep in mind. First of all, when I look at this problem, I see that there are three completely independent parts. I see there's a numerator, I see there's a denominator on all of these, and I also see that the signs alternate all the way through. So if we start with just the numerator is 1 all the way through. So I'm just going to put a 1 on top. Now, in the denominator, I can see that my numbers are going to change from 1 to 8 to 27 to 64. So I'm going to need a formula so that when I plug a 1 into that formula, I get a 1. When I plug a 2 into that formula, I get an 8. When I plug a 3 into the formula, I get a 27. And when I plug a 4 into the formula, I get a 64. So with a little bit of just trial and error maybe, you can see n cubed would be a perfect fit. By plugging the numbers 1, 2, 3, 4, etc. into n, it does give you the respective denominators. And then the other part that I would have, the third part, would be the alternating signs. Now, for sequences, there are two different alternators. The alternator's only purpose is to alternate the sign. You can have an alternator that looks like this, or you can have an alternator that looks like that. Now remember, we're starting here at n equals 1. So when we plug our 1 in for n, you can see in that first alternator, it would start negative and then go positive, negative, positive, all the way through. The reason why it changes signs is because your exponent here being even or odd will force the alternator to be positive or negative. In that second alternator, again, starting at n equals 1, by plugging a 1 in, you could see you would start positive and alternate the other way. So for us, our first term is positive, so we would want to use this alternator right here. So you can either put that on top if you'd like, or I'm just going to go ahead and write it next to the side. So this formula right here, this is going to generate the terms of the given sequence in the order that they're given as well. So these are great problems. You can always check your answer. Just run n equals 1, 2, 3, 4 all the way up, and you can see that you should get those terms in that order. Now, the second example that we're going to look at is actually going to be another one similar in that it's our job to write the formula that creates these terms in this order, but we're told to use a recursion formula. So recursion formula, remember, is generates the terms using the previous term. So what's easiest to do in these problems is actually just write it into words. You can see that we got the 25 from the previous term by subtracting 5. You can see that we got the 20 from the previous term by subtracting 5, and you can see that we got the 15 from the previous term by subtracting 5. So what do? We subtract 5 from the previous term. And then if you remember a few minutes ago, we denoted that previous term as a sub n minus 1. So our recursion formula would be subtracting 5, from the previous term. And if you remember also, that last problem we worked with recursion, of the given recursion formula, they had to tell us where to start. So now it's our job to tell the reader where to start. And the only way you're going to get these terms in this order is if you start at 30 and subtract 5 from the previous term. Once again, like the last one, it's great to check your answer on this. You can guarantee that you're correct by just throwing in a few numbers and making sure it checks out.